Good morning, everyone. My name is Jan Rak, and together with me is Professor André Assis from Brazil. And it's a great pleasure for me to invite you for our online conference. It's called Scalar Electromagnetism 2023. It's a one-day online conference completely free because of our generous sponsors and NAMI-Tech company, right? So it's a really great pleasure to have a chance here to discuss open question in electromagnetism. Right, so why we are here, why we organize this conference, it kind of reminds me the history. I actually worked for many years at CERN. That's the Central European kind of research for nuclear science, and in Switzerland. And I remember a couple of years ago, I visited the CERN library as we're doing very often, and then I find the book Nonlinear Optics, where I found several papers of Tom Burden, Paul LaViolette, and many others. And it brought me to the very strange field of the physics, which goes beyond kind of what we were doing at CERN and what is the kind of main topic of research in the mainstream. And I realized that there are many new dimensions what one can kind of study, and that the field of electromagnetism is not totally old and closed field as I thought, right? So this kind of generates some curiosity of me, and then I realized that there is also a big kind of society of scientists which are also thinking in the same direction, like, for example, Professor Assis. So let us start with the first contribution to this one-day conference. And the first speech is would be my presentation, and I will be speaking about the beyond standard electromagnetism. So, can you bring my slide, please? Right. So the title is Beyond Standard Model of Electromagnetism, and as I said, it's motivated by the ideas that although many people think that the electromagnetic theory is 150 years old, so it doesn't make sense to think about, I will try to kind of prove you that it's not the case. So the next slide, please. So this is a picture I found in the internet some while ago. And it somehow demonstrates what resonates with the mainstream scientists and the laymen also, that we are kind of confirming the Einstein theory again and again. We discovered the gravitational wave, black holes, we can recreate the temperature greater than the sun core, and so on and so forth. And somehow the title was that we are the proud generation of the 21st century to be able kind of to observe these successes. I think it's quite impressive. It's true, I'm not saying it's not, right? It's very impressive. Next slide, please. And it forms what is known as a standard model. In the high energy field, we call the standard model of particles and particle interactions. So, as I said, it's very impressive, but there is also fact that there seems to be that the practical implication seems to be somewhat limited, right? I even find a very interesting paper of Chad Orzel in Forbes 27. He said it's the standard model is the greatest wrong theory in the history of science. I think it's really interesting. Also, I know that I don't want to kind of discourage people that, you know, I think that standard model is very complicated and nice theory, but there are some limitations like a strong CP problem, hierarchy problem, neutrino oscillation, and everybody knows that the gravity, the treatment of the gravity is incompatible with the quantum mechanics, right? So, next slide, please. I would say there is also some other limitation, more kind of psychological, that the standard model is quite restrictive in a way that there are no possibility to have over-unity systems, no superluminal propagation, no longitudinal and scalar waves. This is a subject of the discussion, right? So the next slide, please. Right, so we all know that the 21st century is kind of full of new technological developments, and it's mainly due to the electromagnetism. Everybody has iPhones and whatever, so we know that it works perfectly, and due to the quantum physics, semiconductor, quantum computers, and so on. But as I said, one of the kind of premises is that the so-called coefficient of performance, COP, is always it's as defined as a energy what the system can produce in terms of heat or whatever, divided by the input energy, is always smaller than 1, right? So that we say that the over unity devices with COP larger than 1 are impossible, right? The next slide, please. On the other hand, we have the solar panels. I found that in some paper from 2008 where the solar energy, kind of solar panels, can deliver the COP device much larger than 10, for example, right? So it's kind of irony. I said that the over-unity systems are prohibited, although almost everybody has a solar panel which has a larger COP larger than 1. And to my opinion, it's not really a rather scientific approach, but it's more kind of psychology, that the people are kind of convinced that no over-unity is possible because it's related to narrative. Now, obviously, we know why the COP in the case of the solar panel is larger than 1, because the solar energy, right? But who said that there are no other sources like vacuum, zero-point energy, and so on, right? So the next slide, please. Right, so the current paradigm, I would say, is the scheme of current paradigm looks like that. We have the electromagnetic theory, which I would call is mother of all, the classical electromagnetism, because all other kind of like the Einstein theory of relativity or quantum mechanics in some way are kind of derived from the electromagnetism. Then merging the relativity and quantum mechanics, we get to quantum field theories with two flavors, quantum chromodynamics and QED is quantum electrodynamics. And there is also a separate path, which is the general theory of relativity, which is the only kind of part of the standard model which copes with the gravity, right? And these two flavors, the QCD and QED, that's the main research topic at CERN, where I spent more than 30 years, right? So what do we think about this classical electromagnetism? I would say it's a pillar of all other kind of scientific fields. So it's unshakable, so to speak, right? If we want to kind of change or do something about the electromagnetism, then all the other fields are also kind of in jeopardy, right? And so also the fact is that the theory is born 150 years ago, so there is nothing to add, right? So what is, if 150 years we know this theory, so who will care about this anymore, right? So please go to next slide. This is just the summary of what I said, the special theory of relativity, which I also will be discussing here, is kind of, in layman terms, is kind of characterized by the time dilation and length contraction. I will not go into the detail now. And the gravity and quantum field theories are described here, so I think we can go to the next slide. Right, so let me now go back these 150 years and go back to 19th century, where the classical electromagnetic theory was completed, and it was an amazing work of James Clerk Maxwell, who unfortunately died very young. I think he was of the age of 38, I think, right? And here are the actually eight partial differential equations for the electric E and the magnetic fields, right? So these E and B are electric and magnetic fields, which are three-component vector fields, right? So the first two are scalar equations describing the Gauss law for electromagnetism, for electric and magnetic fields, and then we have Faraday and Ampere's law, which are vector equations, and so altogether we have 8 equations for 6 unknowns, which is already kind of problematic, as we will see later. Go to the next slide. So this was all known. I think all physicists and electrical engineers are very well aware of all this, but there is a less known fact is that Maxwell formulated his equation in quaternion algebra. He presented actually the results in quaternion. I will be speaking about that later. And his equation were actually 20 equations for 20 unknown. Then he also introduced a displacement current, kind of to explain, how come that the current can also travel through the empty space in layman words. And his equations also admits the scalar field solution. So that's also the reason why the Maxwell theory was largely ignored at the time, until Heinrich Hertz in 1888 has proven an existence of electromagnetic waves, radio frequency waves, which was a great achievement. And there is very interesting kind of part of the history which didn't make the path into the textbooks, right? That when Hertz discovered the electromagnetic waves, he also proved that the electromagnetic waves are of the transverse character. It means that the electric and magnetic vectors are always perpendicular towards the direction of the propagation. However, at the time, Nikola Tesla, which will be mentioned here several times later, was trying to replicate the Hertz experiment, and he was unsuccessful. And he discovered some other properties of the radio frequency waves, came to Hertz, tried to convince him that his conclusion about the transverse character is incorrect, and somehow they have a long debate, but at the end, as we all know, the history decided in favor of Hertz, and the Tesla work was largely ignored until these days, right? Next slide. So this is just a small example how the Maxwell wrote his equation before the vector algebra. So he wrote, for example, this is a continuity equation, and he wrote it in individual terms. Nowadays we use the vector notation, right? And then later the Maxwell quaternion notation looks like that. I cannot even read the characters, right? But it's what are the quaternions? I don't have a time to go into these details, but the quaternions are generalized, so to speak, complex numbers, where the complex numbers are very known two-dimensional numbers, where the other dimensions, the imaginary axis is defined by square root of -1, right? And the quaternions are generalization, four-dimensional generalization, which uses 3 imaginary unit ijk, and Hamilton finds some kind of relations such that the quaternion forms the divisible algebra, which are, as in contrast to complex number, the quaternion do not commute. There is a lot of very interesting things we can say about quaternions, but we have to move on, maybe next time. So the quaternions were too complex for Maxwell contemporaries that time. So although, to my opinion and opinion of many other scientists, the quaternions open really a door to new electrodynamics, but quaternions were overlooked by mankind, I would say. Nowadays, we all use the vector calculus, and I think it's really a pity, because as far as I know, that the quaternions are essentially used only by programmers, right, in the 3D kind of rotation programs, right? So what's happened in the era of Maxwell, that people kind of did so-called dequaternionization or vectorization of the quaternions, meaning that the four-dimensional quaternions, people realized that the complex part, the imaginary part of quaternion forms three-dimensional quantities. So that was a precursor of the 3D space kind of vectors, right? And then also people abandoned this imaginary unit, square root of -1, and at the end the vector algebra was born. Algebra, if you go to next slide, please, that's kind of overkill for the message, but some people think that we say the vectors is not divisible algebra, so there is no multiplication of vector, right? But we have the cross product, the vector product, but the vector product is so-called pseudo-vector because under the parity transformation it does not change the sign, right? So it's not a vector. Actually, I realized that the cross product of the three-dimensional vector gives an object which has also 3 dimensions, is a pure coincidence. The cross product of two vectors is actually the rank 2 tensor with 3 independent coordinates only in the 3-dimensional Euclidean space, right? So for example, in 4 dimension is also the rank 2 tensor, but it has 6 independent coordinates. So the cross product is not a vector, it's a tensor, right? So the next slide. So at the end, we have now, that's the situation where we are now, to my opinion, that we have Maxwell Heaviside equation. So people are used to say it's Maxwell equation, but it's really different. These are the equations which Gibbs and Heaviside re-express in the modern vector form. And there are some aspect of the Maxwell Heaviside theory which is, to our opinion, at least my opinion, problematic. And one of the most important problematic aspect is that the classical electromagnetism and the special theory of relativity is not a generalization of the lower order theory. It's not generalization of Newtonian physics. There is no invariance of the special relativity and classical electromagnetism with respect to Galilean transformation in the low relative speed limit, right? So this is, to my opinion, a very important point. Then also that the classical electromagnetism is overparameterized, 8 field equation for 6 unknown. We know how to deal with that. There are some tricks and so on, but it's, to my opinion, it's something alarming as well. Then there are some known fact that Lorentz force law violates the Newton third law. We will have a discussion about that later. Electrodynamic energy momentum, 4/3 problems, very known. QED and QCD are, the quantum electrodynamics and classical electromagnetism are also inconsistent in a way that force field in classical electromagnetism are electric and magnetic fields, but in quantum mechanics we are speaking about the scalar and vector potentials, right? So what is real? Is it the force field, electromagnetic, or is it the potential? So somehow this is very, I would say, fuzzy thinking, and I'm glad that we have here Professor Andre Assis. He will be speaking about the completely different approach from the point of view of Weber electromagnetism. There are also some experimental facts which are, to my opinion, very difficult to get in harmony with Maxwell equation, like Sagnac effect, Maxwell-Lodge effect, and so on and so forth, right? So next slide, please. Right, so we are speaking about the paradigm shift, and this is also our agenda for today's meetings. So there are many attempts to rectify, for example, this broken Galilean symmetry. We will be speaking here today about the extended classical electromagnetism. I like also the notion which is the neo-Hertzian theory by Thomas Pepys. He wrote excellent books and many papers. One book I would recommend to everybody, Old Physics for New. It's really amazing piece of research. Then the other possible, look, I'm not saying that this is all what exists, but this is all what I know and I like. For example, the biquaternion formulation, for example, I think Andre Wasser, many papers like application of biquaternion in physics, very interesting. I will mention a couple of things here. Extended classical electromagnetism, Koen van Vlaanderen will be speaker this afternoon. He will be speaking about the generalized classical electrodynamics, and then Professor Andre Assis about Weber relational electromagnetism. Very brilliant ideas, right? So next slide, please. So let me spend a couple of minutes now and to contemplate about this. Is Maxwell Heaviside and Einstein theory relatively covering theory meanings that in the limit where the relative velocities are small, then it's very natural requirement that in the low speed limit the new theory becomes the same as the old, right? So we call it covering or complementary principle, right? And here I mean the old is the classical old Newton physics with Galilean transformation, and that's what we kind of is a part of our everyday experience, right? We are living in the world where we are kind of experiencing the Newton physics, not the relativity, obviously, right? And then the new physics, I mean, is the Einstein's relativity or the Maxwell equations, which are related to Lorentz transformation, and that's the physics we are experiencing in accelerator physics, astrophysics, and so on. So it's kind of beyond our everyday experience, but it's there also, right? So the next slide, please. So the Galilean transformation, sorry for bothering you with such a simple things, but this is as simple as it's written here. In Newton physics, the time is absolute, right, which is very interesting. We can discuss that some other time. What does that mean? And space is also kind of absolute, and we have this very classical addition of velocities, right? So if you have in one reference frame some moving object like this fly, so from the reference frame which is moving with respect to that one, the velocities of are just adding as in the usual way. Everybody knows that, right? So next slide, please. On the other side, special relativity is somewhat more complicated, is characterized by Lorentz transformation, which is a linear transformation which mixes the coordinates, right? The spatial and time coordinates are intermixed, as you can see here. We have a Minkowski diagram which represents what is the invariant object in the transformation. So in the classical Galilean transformation, the invariant object is a circle. Here we have the hyperbola, right? So it's, I think the special theory of relativity is not kind of difficult to understand. It's an engineering subject, but let's move on now. Next slide, please. Here is again the Galilean transformation, and I express the spatial and temporal derivative, how they behave under Galilean transformation. So the first equation is the differential equation for the Nabla operator, very known, right? And because the time is absolute, the ordinary time derivative in the reference frame which is moving with respect to the other gives that the ordinary derivative also is invariant, so to speak, but the partial differential derivative with respect of time is different, right? So in this case, if we write the differential equation for that, we have an additional term, right, in the partial differential equation is very easy to derive, but there is extra terms which kind of characterize the relative velocity of the observer and the field which is observed, right? So the next slide, please. And this is very important observation because the Faraday observed, actually the Faraday law can be written in this form, right? The circle integral of the electric field is equal to time derivative of the magnetic flux, and the time derivative, which can be used by Stokes' theorem as a two-dimensional integral over the surface. But the important point is that this derivative, and I think Faraday also formulated that in that way, that the time derivative is an ordinary derivative, right? However, somehow Thomas Pepys did a very good job. He kind of tried to search all the possible literature, classical, Jackson books and so on, to find where the notion of the partial derivative is coming from, and he found that everybody somehow assumes that the ordinary partial derivative is the same, and nowadays we use the partial derivative. But this is exactly the term which spoils the Galilean transformation. Let me go first to the next slide, please. As I have presented these partial derivatives, one can see that the kind of the space-time symmetry in the concurrent theory is due to the use of the partial derivative, right? So in this way, we have a 4-vector which can be kind of transformed with respect to Lorentz transformation, but if we use the total derivative, the ordinary derivative, then we have extra term which spoils the spatial symmetry. But on the other side, the use of the ordinary derivative keeps the invariance with respect of the Galilean transformation. So if you go one slide back, please, right? So then the notation which is now used in all textbooks and so on, that the partial derivative of the integral over the magnetic field doesn't obey the Galilean invariance, right? But it's Lorentz invariant. But if we go back to what Faraday observed and what it should be here is the ordinary derivative, then we restore the Galilean invariance, but we lose the Lorentz invariance, right? So it's kind of, to my opinion, very alarming kind of situation that we can choose either we prefer the beautiful space-time symmetry, but we don't have a Galilean invariance, meaning that in the low speed limit, the Maxwell Heaviside equation do not comply with what we observe in everyday lives, right? So next slide, please, and then the next slide. There is very important, very interesting paper, a historical fable with a pedagogical moral. I will really recommend Gemmer and Stachel. Very nice paper where they were very polite and they kind of proven that if we use the Maxwell equation with the amperes equal to 0, right, then this kind of settled equation is invariant with respect to Galilei transformation, right? But if we add the term with the partial derivative, then the Galilean transformation is lost, right? I think it's very interesting point. I also spent some while ago in 2019, we have a conference in Prague here with the title Beyond Einstein Relativity, right? Where I also discussed that even the special relativity is not invariant in contrast what is said in all textbooks that the special relativity is invariant with respect to the Galilean transformation, but it's not, because this is a Lorentz transformation, right? And when we say if the relative velocity is very small, then beta is equal to 0, let's say, and the gamma factor is equal to 1, right? The typical Lorentz factor. but it's not the correct approach, right? The low speed limit comes from the Maclaurin or Taylor expansion of the gamma factor, right? And if we do that, then we realize that if we neglect all the terms which are higher than quadratic, quadratic and higher terms, then we are actually left with the transformation which is written here, which is not t prime is equal to t, right? So if we go to the next line, to make this more transparent, right, we can use also a time interval transformation instead of the time coordinate itself. And in terms of time interval, I see that in any other coordinate frame, the delta t prime is equal to delta t plus v times delta x over c squared. So there is a small addition with respect to small kind of addition which doesn't exist in the Gaussian transformation, which tells you that if you have a pair of events, you can always find the pair of events which is simultaneous in one kind of reference frame, right? But in all other reference frame, also they are moving with very small relative velocity, that these simultaneous events will never be simultaneous in any other reference frame. So to my opinion, that's a very big problem, because in Galilean transformation, time is absolute. So it means that if in any reference frame, two events are simultaneous, they are simultaneous in any other reference frame, right? But in Lorentz transformation, the simultaneous pair of events it's never simultaneous in any other reference frame. Also, the reference frame is moving with very small velocity, right? So that's what it is. We go next slide. Right. Let me now inject some other ideas. I have mentioned that this rectification of the known problems is also some theorists develops a quaternion or biquaternion formulation. So what are the biquaternion, which I like a lot, is yet generalized quaternion, so to speak, where instead of the coefficients, in the case of quaternion, the coefficients A, B, C, D are real numbers. Now they are complex, right? So if we use the if we use the complex coefficients in the quaternion description, then we get 8-dimensional hypercomplex numbers, right? It's kind of weird maybe for some, but it has very promising consequences for formulation of the theory. I'm not saying that this is the solution, but this is a solution I like a lot, right? So I don't want to load you with too many details, but the differential operators in the big quaternion forms, like nabla and nabla conjugate, D'Alembert operator has this form, right? So if we go to next slide, then we can define the electromagnetic quaternion electromagnetic potential as it's written here, and the quaternionic current density J is defined like that. And with this definition, we can differentiate and find the solution, and the goal is to find the equation, the wave equation. So go to next slide. So if we use the rule for quaternion multiplication, then we write the nabla of the A potential, so to speak. Then you see that the results is kind of in a simple way, which is very interesting, shows the parts which reflects exactly the gauge kind of formulation of the electric field from the vector potential and scalar potential, right? Then we get a part which describes the magnetic field, and then we have some other parts which we call S, and that's what we now be calling the scalar field. Next slide, please. So this is a summary from the previous slide. So when we use this big quaternion formulation, we got the classical, so to speak, equation for electric magnetic field, but we got the extra term which is called scalar field, right? So this kind of gradient of the the Big-Quaternion gradient of the potential can be written in a simple way, which is this has a scalar field and some complex part, right? So if you go to next slide, then you can show that using this kind of simple manipulation in the Big-Quaternion space, you can derive kind of the Maxwell, kind of classical Maxwell equation in different form, but these three equations are identical. Go to next slide, please. And then with, if we calculate kind of the double differential, right, kind of the Laplace operator, then we got something which looks like that, right? So it's a quite complex equation, but from that we can go to next slide, please. And from that we can kind of find a version of the generalized Maxwell's equation with additional field, which we call scalar field. So this is very classical, you know, results of the classical Maxwell equation, but here the Gauss law, we say that there is an additional small extra field in red, which is the partial differential derivative of the scalar field, and here we have a gradient of the scalar field, right? So if you go to next slide, these additions have kind of the strong consequences, because if we go back and kind of recall the nature of the radio frequency wave or electromagnetic waves, the solution of the wave equation, Maxwell's equation, give us the transverse character of the electromagnetic waves, and it's due to the fact that the divergence of the electric field is equal to 0, right? But now in this new equation the divergence is not 0, so because of this extra term, so as a consequence, we see that there is a possibility in this Big-Quaternion formulation that there are longitudinal waves, that these longitudinal waves are possible in the frame where the, and we can write it, it's just in the frame, which we can kind of set as we want, where the Ex and Ey, the components of the electric field, are 0, we get kind of this longitudinal equation for the scalar field, right? So if you go to next slide, so this is a depiction, you know, so that's the classical picture of the electromagnetic waves where the electric and magnetic field are always perpendicular to direction of the motion. But now we have a longitudinal wave where, for example, in the case where the rod E is equal to 0, then the magnetic field kind of doesn't have a time derivative, right? So it's kind of, we also call it the magnetic field is frozen in time, right? So this brings me to the conclusion, so to speak. It's kind of difficult, so I try to explain here that there is a possibility to rewrite or to have a theory which admits the scalar field and longitudinal waves. I didn't discuss that into the details, but this Big-Quaternion and other formulation also reject the gauge freedom, right? In this theory, the potentials are not anymore freely gauged, so you cannot change the potential freely, so the potential is fixed, the Lorentz gauge is gone. And this freedom really allows, you know, the different solution like the scalar waves and so on, and the longitudinal waves. So if we go to next slide, obviously at the end is the experimental which decides, right, not the theory. So thank you for your attention.